All right, Chemistry 3101. We said we were going to start off with some practice today. So we're going to start out by taking a look at question 8.59, 8.69, and then there's a big one here, which is 8.70. And these questions are a great way to really just kind of practice all the different reactions that we've looked at in the class. All right, so with 8.59, let's start here. I'll start here. And could anybody tell me, you can see that if I highlight these two carbons, if I highlight this carbon in red and this carbon in blue, you can see the carbon in red has two hydrogens attached to it, and the carbon in blue has none. So this reaction here, where I have the question mark, would this be a Markovnikov addition of HBr, or would it be an anti-Markovnikov addition of HBr? Could anybody answer that one? Would it be Markovnikov or anti-Markovnikov for this first one? Don't be shy. Yep, exactly. Thanks, Lauren. It's anti-Markovnikov. So what does that mean? It means we're going to need HBr and an organic peroxide as well. There you go. All right, and that mechanism is not covered until chapter 10, so you don't have to worry about the mechanism, but you do have to know that this is anti-Markovnikov addition of HBr. So that means that the next one is a Markovnikov addition of HBr across a double bond. And so the reason it proceeds with Markovnikov regioselectivity is because after the proton transfer, you end up forming this tertiary carbocation, which is the most stable carbocation. So we add our hydrogen here. And so then the bromide comes in as a nucleophile. And so you should be able to draw that mechanism. So I'll put a star by that one. You should be able to draw the mechanism of Markovnikov addition of HBr across a double bond. The next one, again, you can see that the hydroxyl group is being added to the more substituted carbon. So this is also a Markovnikov addition. This is Markovnikov addition of water. And to add water across our triple bond, or across our double bond, we're going to need H3O plus, right? Aqueous acid. And again, that's going to give us that same old tertiary carbocation like this, and then water's going to come in as a nucleophile. We do a proton transfer, and we end up with this alcohol. All right, the last one, this last one here, I'll put a question mark by it. It is an anti-Markovnikov addition of water. Could anybody tell me what the first reagent would be for an anti-Markovnikov addition of water across a double bond? It doesn't have to be fancy if you type it in the chat, even if you just give me part of it. I'll know what you mean. For anti-Markovnikov addition of water, what is our first reagent that we need? Can't just use H3O plus. Okay, so for that one, we're going to need borane and THF. All right, so we're going to need borane and THF. And then in the second step, we're going to use hydrogen peroxide and sodium hydroxide. So keep in mind again that this is anti-Markovnikov in terms of the regioselectivity, but in terms of the stereoselectivity, it does syn addition. Now, there's only one stereocenter formed here, so it's not really pertinent, but we get a syn addition of the proton and the hydroxyl group. All right, so we finished that one. Let's move on to 8.69, and it's just a little bit more practice of the same thing. So this next one here, we're taking an alkene and we're converting it to an alkane. And so that's a hydrogenation reaction. And for a hydrogenation reaction, we're going to need hydrogen and some kind of metal catalyst. We can use palladium, platinum, or nickel. I'll choose platinum just for fun. But again, this is hydrogenation, which also occurs via a syn addition. Again, it's not relevant in this one because there's no stereocenters in this product. But it is a syn addition. All right, the next one is halohydrin formation. So halohydrin formation. And for that, we need bromine, which is going to be our electrophile, and then water is going to come in as well. All right, and keep in mind that this is going to proceed through the bromonium ion. So you need to know that mechanism. So here's my bromonium, which looks something like this. Here's my methyl group like that. Okay, and then water is going to come in as a nucleophile, and it's going to attack the most substituted carbon like this, and then you're going to end up breaking this bond, and you end up, after a proton transfer, with this compound. All right, so there we go. And keep in mind that the halohydrogen formation proceeds via anti addition. So you have to know the regioselectivity, that the hydroxyl ends up on the most substituted carbon, and you have to know that it's anti-addition. If the hydroxyl is on a wedge, then the bromine would have to be on a dash. Okay, the next one, could anybody give me a reagent for the next one? For this one, even if you just give me one of the reagents, because this is a two-step process. This is called oxidative cleavage. Could anybody, there you go. So DMS is the second one. Absolutely, thanks, perfect. So yes, reagent number 2 would be dimethyl sulfide, and the first reagent would be ozone. All right, so we need ozone to do an oxidative cleavage. And we went over the skill builder that, so I think it's skill builder 8.8, where he explains how to do these kinds of problems. So what you do is you erase, that didn't work very well, but you erase the double bond. I erased too much of the double bond, okay, like that. And then if you just put oxygens on the end, that gives you the final product. And so you can see that this compound that I just drew, no matter how ridiculous it is, it's identical to this compound. You can see that you have the ketone here, and then you have the aldehyde here. Anyhow, hopefully you'll find that skill builder useful. And again, we went over that in class, so I'll just get rid of all that. Okay, so that's ozonolysis. So ozonolysis. And the last one is an anti-Markovnikov addition of water across a double bond. Again, it's the whole idea of the rich get richer, right? So this carbon has a hydrogen on it, so it's richer in hydrogens. This carbon in black has 1 hydrogen. This carbon in red has 0. So if you were to get this product, okay, if you made this product, that would be a Markovnikov addition, because the rich would be getting richer with a second proton. So for a Markovnikov addition, where there's no carbocation rearrangement, you just need aqueous acid. So just write H3O plus. Whereas if you want to do the anti-Markovnikov addition, we went over that earlier today. The step 1 is going to be borane and THF. And step 2 is going to be hydrogen peroxide and sodium hydroxide, just like that. Okay. Okay, perfect. Perfect. All right, now that we've got that done, let's try this this big one here, 8.70. I recommend printing a copy of these out and just trying them over and over and over, and eventually the reactions will sink into your head. But the first one, you can see that we're breaking the carbon-carbon double bond here, right? There's a CH2 group at the top, and you're going to slice that off completely by breaking the bond here, okay? So you can clearly see that this is an ozonolysis reaction. And we just reviewed that the first step is ozone, the second step is DMS. All right, next one is an anti-Markovnikov addition of HBr. We covered that in detail, so that's HBr followed by an organic peroxide. And the next one is an anti-Markovnikov addition of water, and we've seen that twice already this morning, so borane and THF followed by H2O2 and sodium hydroxide. And again, sometimes in things like the MCAT or ACS, sometimes they'll write it this way. They'll put step 1 is B2H6, and step 2 is H2O2 and hydroxide. So they'll actually leave out the sodium cation. Sorry, that looks like the letter N, so let me fix that. There we go. They'll just leave it out. But again, I told you that borane THF it's the same thing as saying B2H6. They both serve the exact same function. Are they exactly the same? I guess not, but they serve the same function in terms of their reactivity. The next one is a dihydroxylation, but there's no stereocenters. So no stereocenters. So you could literally use any of the dihydroxylation techniques that we learned. You could use osmium and a catalytic amount of osmium tetroxide and NMO. You could use osmium tetroxide followed by sodium bisulfite. That will work. And one that we went over quickly was the potassium permanganate. So for that one, we write potassium permanganate, KMnO4, sodium hydroxide, and it's done at a low temperature. Like you put some ice around the reaction flask or something, and so we just write cold. And the reason why it's usually done at a low temperature is because KMnO4 is such a strong oxidizing agent. If you put it in the presence of any other functional group, it will oxidize that as well. The next one is a halohydrin formation, and we've seen that already today. So this is again halohydrin formation like that. So we're going to use bromine, Br2, but we're going to use water as a solvent. And of course, the regioselectivity is that the hydroxyl ends up on the more substituted carbon. The next one is a Markovnikov addition of water. So we're going to do this like this. So just aqueous acid. And again, this is a Markovnikov addition. All right, next one. Let's just look at this one. So we're taking the alkene. We're doing a Markovnikov addition of HBr. And so for that, we're going to need just plain old HBr, right? Because it's just a Markovnikov addition, nothing fancy. The next one, going from here to here, we're making the Zaitsev alkene. So this is the Zaitsev, okay? I'll just put Z-A-I-T like that. So instead of using a hindered base, we'd use an unhindered base like sodium ethoxide, and that would give us that. If you wanted to make the Hoffman product, you'd use a hindered base like DBU, DBN, or potassium T-butoxide, and that would give you that, what we call this an exocyclic alkene, right? Because the alkene is leaving the cycle or it's outside of the cycle. Anyhow, I think you pick up on that word. Next one here, this is just a hydrogenation. So this one here, we're taking the alkene, converting it to an alkane. And so we're just going to put H2. I'm going to use nickel as my catalyst this time. Okay, now we've got two hydroxylations. We've got a syn dihydroxylation, and we've got an anti, I'll use a different color here. We've got an anti-dihydroxylation. Okay, so for syn dihydroxylation, why don't we use osmium? So we'll put a catalytic amount of osmium, so OSO4. I like to write catalytic. It's not always put that way in the textbook. And then NMO, which is your co-oxidant. Whereas if you want to do an anti-dihydroxylation, that's a two-step procedure. So first step is MCPBA, or some kind of peroxy acid. And the second step is H3O plus, like that. So in terms of mechanisms that you need to know, what are the mechanisms that you need to know? I'll use a green star for this one, okay? The ones that you would need to know would be, the formation of the bromonium ion. We covered that in detail. A Markovnikov addition of water across a double bond. A Markovnikov addition of HBr across a double bond. An E2 reaction, whether you get the Hoffman product or the Zaitsev product. And then the last one, I guess, would be the second step here, right? Because remember, after the first step, when you take the alkene and you treat it with the peroxy acid, you end up making the epoxide. And we talked about what an epoxide is. That's when we have a three-membered ring, okay, like this. Okay, so you end up with the epoxide like that, and then you need to know the the mechanism going from here to here, right? The first step is a proton transfer, et cetera, et cetera. So there you go. So you would need to know this part of the mechanism here, okay? And this are the same thing. All right. Are there any questions about any of the specific reactions in here? I realize it takes a while to digest them all and to have a good understanding of them. But the best way, in my opinion, to do it, and I think that based off of historical evidence, the best way to do it is to just practice it over and over. All right. So there we go. So that's a little bit of practice on chapter 8.